The one-sample t-test. In this tutorial, we will conduct a one-sample t-test. You use this procedure when you have interval scale data and want to test the research hypothesis that the population mean differs from a specified value. Let's do an example. Assume that AAA claims that cars driven in the US have an average horsepower of 100. You, however, believe that horsepower of cars differs from this value, being either less or more than 100. Your research hypothesis is therefore that horsepower is unequal to 100. You then collect a random sample of American cars. Our sample here contains 406 observations. To do the one-sample t-test, you do the following. Go to Analyze, Compare Means, One-Sample t-test. Enter the horsepower variable in the box of test variables, and then specify the test value. Our null hypothesis was that horsepower is equal to 100, so we enter that. Let's click OK. Although we handed out 406 questionnaires to car owners, only 400 responses are included in this test. That's because 6 car owners refused to answer the question and have missing values. The mean horsepower in our sample is 104.83. SPSS uses the standard deviation of our sample, in our case 38.522, to estimate a standard error. In our case, that's 1.926. Based on the standard error, it calculates a t-value. This t-value measures the distance of our sample mean from the hypothesized population mean of 100 in standard errors. In other words, the t-value tells you how far our sample mean is from 100, and it does not give us the distance in inches or meters, but in standard errors. In this case, the sample mean is 2.509 standard errors from 100. That the t-value is positive, not negative, indicates that the test value is greater than and not smaller than 100. The significance level shows that 0.013 or 1.3% of the sampling distribution are in both tails of the distribution. Half of that, 0.65%, are in each of the tails. Let's now leave SPSS and look at the sampling distribution. It looks like this. First, the distribution is based on the assumption that the null hypothesis is true. So the population mean under the null hypothesis is in the middle. It is 100. Our sample mean of 104.83 is 2.509 standard errors to the right. .65% of the sampling distribution are in the right-hand tail. If you mirror this by going 2.509 standard errors to the left, you get to the value 95.17. And 0.65% of the sampling distribution are in the left-hand tail. The two areas in the tail add up to 1.3% or 0.013 as shown in the SPSS output. You see that our sample mean is really quite far out in the tail. Only 1.3% of the distribution have means that are even more extreme than ours. If the population mean is really 100 as assumed, it is very unlikely that one would get a sample mean or a sample with a mean such as ours. We therefore reject the null hypothesis that the average horsepower of cars in America is 100, and we conclude that AAA is wrong. And note that usually you reject your null hypothesis whenever the significance value in the SPSS output is 0.05 or less. Now in our example, we just hypothesized that horsepower was unequal to 100, without saying whether it was greater than 100 or less than 100. We therefore conducted a two-tailed test and looked at both tails of the sampling distribution, and the areas added up to 0.013. Alternatively, you could hypothesize that average horsepower is greater than 100. In this case, we would only take into account the right-hand tail of the sampling distribution. Our significance level then is not 0.013, as given by SPSS, but 0.065, or half the amount.